Hello, so welcome to this video. So in this video we're going to be looking at how the sun produces energy. This is a follow-up to the video of E equals mc squared. In the previous video we looked at deriving E equals mc squared and understanding it using relativistic principles. Now that video was in a relativity playlist. This video is going to be more in an astrophysics playlist because it's about applying E equals mc squared. We're going to take that as true and we're going to show that if we use E equals mc squared to understand how much energy the sun can release if it converts mass into energy during the process of nuclear fusion, how long the sun can remain in its current main sequence phase where it's fusing hydrogen nuclei in its core. So that's the main purpose of this video. We'll also be looking at other historical ideas of how the sun might produce energy, and we'll also be exploring a kind of hypothetical possibility that perhaps, we should consider, for example, maybe the sun is just made up of hydrocarbon molecules and is producing energy by combustion in much the same way that we produce energy on Earth by burning very large hydrocarbons like candle wax. So we're going to be exploring kind of the possibility that maybe the sun is a ball of hydrocarbons. We know from atomic spectra that's not the case, but it's worth considering, alternate hypotheses. And also it's kind of cool to consider if you had a hydrocarbon star, how long could it be stable for? Now this video will be mainly using lots of kind of arithmetic with a dash of chemistry, because to work out how much energy the sun could produce through combustion if it was made up of hydrocarbons, we need to use chemistry. And so there will be a tad of chemistry. If it's been ages since you've done chemistry, don't worry, I'll be kind of describing what we need when we get there. But hopefully it'll be kind of a bit of fun and exciting use of chemistry because we'll be applying it to astrophysics, which is definitely isn't something that is often done in the core syllabus in chemistry, but I think it's kind of cool. So this is going to be mainly an application of E equals mc squared, but with a dashing of chemistry and history all thrown into the mix. So we're quickly going to go through some possible historical explanations for how the sun could produce energy. And these are legitimate ideas that were kind of proposed. At least the first 2 points on this slide will be. So the first idea was the idea of meteoric bombardment. Essentially that the sun becomes very hot and therefore releases kind of radiation and energy due to the fact that meteorites keep bombarding the sun's surface, and this kind of kinetic energy of the meteoroids then is transferred into thermal energy of the sun. Look, this isn't a ridiculous idea because we know that bombardments of celestial objects happen. One only needs to look at events in the Earth's history to see things from the solar system can collide with planets and therefore also plausibly the sun. The problem is, however, the amount of bombardments the sun would have to endure. Because the thing is, we can determine, based on knowing how far we are from the sun and the amount of, energy we receive on the Earth's surface from the sun, we can determine how much energy the sun is actually emitting every second. And we can also use models to estimate the average kinetic energy of meteorite, and therefore we can work out how many meteoroids would have to bombard the sun for the sun to be able to kind of produce, for the sun to be able to emit the kind of energy it's emitting. Um, but the thing is, given how much energy the sun does emit, uh, the amount of bombardments would mean that there'd be tons of meteoroids around, which would put Earth in a very tricksy situation, and Earth would be bombarded far too regularly compared to what we observe the amount of times Earth is bombarded to be. And also the very fact that we're not regularly, as a human species, worried about catastrophic events due to bombardments on the Earth indicates that actually there isn't nearly enough meteoroids in the vicinity of the sun, and therefore, in at least the reasonably near part of the solar system, for this to be at least the primary way that the sun ends up emitting so much energy. The other thing is, if there were as many meteoroids as would be required, then the total mass of the meteoroids together would actually be significant enough to perturb the inner planets of the solar system off their trajectory, such as, Earth would start Earth would have a different trajectory to what it does. So we can dismiss on kind of, both grounds that as a human species we don't regularly have catastrophic events, life-threatening events to our species, thankfully, and also the fact that, the Earth follows a kind of orbit indicating that there isn't tons and tons of meteoroids within the inner parts of the solar system, to conclude that, the sun can't be releasing thermal energy that it's ultimately gained through the conversion of kinetic energy of meteoroids, which kind of collide with the sun. So, what other suggestions are there? Well, Helmholtz and Kelvin proposed that the sun isn't actually really stable. It looks stable over a short time period, but over a long time period one would actually observe, if one was to put a camera and watch the sun for a very, very, very long time, one would see that the sun is actually contracting. And as the sun contracts, it loses gravitational potential energy, and that gets converted into thermal energy, and thus the sun ends up emitting a lot of radiation and energy, to the solar system. And this idea also seems reasonable, but you can calculate the time scale that the sun will be able to do this for, because again we know how much energy the sun is emitting each second, so we know its luminosity. We can also get a good idea from Newton's law of gravitation and Kepler's laws of motion about the mass of the sun, and given the mass and what we can deduce about its size, we can work out how much total energy the sun would be able to release if it fully contracted, and therefore we can get a timescale for how long the sun could keep producing the amount of energy it is at the rate it is currently producing energy at. If it was producing energy, I say if it was producing kind of the radiation and thermal energy through kind of contracting and the conversion of gravitational potential energy. But that time scale is actually younger than the Earth. So unless the sun has formed after the Earth and the sun is a fairly recent occurrence, this idea doesn't check out. And also we know that organisms that use the sun's light existed at a much earlier much longer ago than the kind of time scale associated with a star that is producing energy through gravitational collapsing. And those are the two kind of main historical ideas before the idea of kind of nuclear fusion came along. Though after those two ideas, there were kind of models like Lane-Emden kind of equations, numerical models, and ideas like hydrostatic equilibrium came about. But there wasn't much kind of new ideas until nuclear fusion about the physical process by which the sun could be producing so much energy. However, an idea that that is contained within these two things is that the sun might just be essentially a large lump of hydrocarbon which is combusting. It's burning. Essentially, the hydrocarbon is reacting with oxygen, and it's this combustion which is then producing energy and heat. Much like how when you light a candle, the wax in the candle, which the wax is like made of a very, very large hydrocarbon, the wax is kind of combusting and reacting with oxygen, and that releases energy. Now, we know, it's worth saying, from spectra of the sun, that the sun isn't predominantly composed of hydrocarbons. The sun is mostly hydrogen and helium. There's very little carbon in the sun, and there's also very little oxygen for combustion to happen in the sun. But it's worth putting spectra to one side, because just looking at the sun, we don't know what it's made out of if we were just going to stare at it with our eyes, and so it doesn't seem a ludicrous suggestion, if we're ignoring like atomic spectra, to propose that maybe the sun is just like a very, very large candle, if you like. So what we're going to do in the next part of the video is we're going to take this suggestion seriously and see, okay, assuming if we give this suggestion the maximum possible chance of working, and we assume that all of the sun is made up of a fairly combustible hydrocarbon, how much energy could the sun release through combusting all of its hydrocarbon material? And that will give us a total energy output of the sun over its entire lifespan, at least in its kind of current stable phase. And then we can divide that by the luminosity of the sun, i.e. the rate at which the sun produces energy, to work out how long the sun could produce energy at its current rate if it was producing energy through combustion. Essentially acting like a very, 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 very large candle. So, as we mentioned in the last part of the video, we're going to take the idea of the sun producing energy through combustion very seriously. Now, the main fuels which are great at combustion are hydrocarbons, because, a way to have complete combustion is to have plenty of carbon and hydrogen available, such that you can make lots of carbon dioxide and water. So hydrocarbons are a good thing to produce energy through combustion. And we might wonder, what's a reasonable hydrocarbon to consider the sun might possibly be made out of? Again, we're ignoring spectra. We're just kind of supposing we have no idea what the sun's made out of. But we know, for example, that not very complex molecules tend to form in space. So what's a reasonably sensible hydrocarbon to pick? And we need to pick a hydrocarbon because different hydrocarbons will have relatively different amounts of carbon and carbon and hydrogen, and therefore the amount of energy we'll get through combustion will depend upon the hydrogen we're combusting. Well, let's assume that we know that it's very difficult to form very large molecules or very complex molecules naturally in space. So we want a very small hydrocarbon. Well, what's the smallest hydrocarbon we can possibly pick? Well, it's a hydrocarbon with only one carbon, and that hydrocarbon is called methane. Now, methane is used in homes sometimes. If you've got, if you use gas when cooking on hob, you might use methane. Methane is also produced, unfortunately, by cows, and for reasons which may be best not to go into on a, hopefully fairly family-friendly video on how the sun might produce energy. But yeah, it'd be rather cool if the gas that cows releases, also the gas which is responsible for allowing the sun to produce so much energy, and thus kind of sustain life on Earth. So it would be kind of cool anyway. But methane is a fairly common hydrocarbon, and because it's common, we have a lot of experiments to go on about how much energy this hydrocarbon would release if it was to be combusted. So that's another good reason to pick it. We can get a sensible, total energy output of our hydrocarbon star if we're using a very familiar hydrocarbon like methane. And methane, we might suggest, might form naturally in space if there's a lot of carbon and hydrogen around, because it's a very small molecule. And for a molecule to form, you kind of need, simplifying this a bit here, but you sort of need the atoms in the molecule to just spontaneously come together and meet, and therefore the smaller the molecule, the more likely it is to just spontaneously form, because you're requiring less atoms to spontaneously come close together. If you want to form a very large molecule spontaneously, well, you need lots of atoms to spontaneously come close together, and that's just very unlikely. So, yeah, well, methane has a fairly high probability of forming, at least compared to other hydrocarbons in space. Now, if we want to calculate the maximum amount of energy we could produce through combusting methane, we use an equation in chemistry. So, in chemistry, they talk about something called moles. Now, a mole is just a certain number of a particular molecule. It's actually Avogadro's number of a particular molecule. So if I have Avogadro's number of, let's say, carbon dioxide molecules, then I have 1 mole of carbon dioxide. If I have Avogadro's number of, of water molecules, I have 1 mole of water molecules. So a mole is just it's a way to, if you like, count the number of molecules, but in terms of Avogadro's number, where Avogadro's number is very large, thus allowing, while there might be many molecules, an unbelievably large amount, we can still say, well, there might be 1 or 2 moles, and easily imagine the number 1 and 2 when talking about the number of molecules. So moles are just a unit which makes talking about the number of molecules a lot more easier to visualise than dealing with the literal number, because the literal number is so large. And there's also something in chemistry called enthalpy, and enthalpy is the amount of energy, usually measured in kilojoules, released in a reaction per mole of the reactant. So in this case it would be the amount of energy released by combusting 1 mole of methane. That's the enthalpy. So because of that definition of enthalpy, the total amount of energy the sun could produce by burning methane would equal the number of moles of methane in the sun times the enthalpy of combustion in methane. Now, the enthalpy of combustion we can get by just doing chemical experiments on Earth. The moles of methane, we have to make some assumptions about the sun to approximate. Well, if we're going to be as kind as we can to the hypothesis of a hydrocarbon star, giving it the best chance to work, we're going to go all out. We're going to assume the sun is entirely made out of methane. So it's literally got all of its mass at its disposal to do this combustion process. And so the way you work out the number of moles of a substance is you take the mass of the substance and divide it by the molar mass of the substance. So we've got here the mass of the sun. It's about 1.99 times 10 to the 30 kilograms. We've got the molar mass of methane, which is 16 grams. You can work that out from the periodic table, because the molar mass of carbon is 12 and the molar mass of each hydrogen atom is 1, and there's 4 hydrogen atoms, so the total molar mass of a methane molecule is 16. And then being careful with units, because molar mass is in grams, but the mass of the sun we wrote in kilograms. The number of moles turns out to be 1.2 times 10 to the 33 moles. So assuming the sun is made entirely out of methane, given its mass, there is 1.2 times 10 to the 33 moles of methane in the sun. So we've got the moles. So to calculate the total amount of energy the sun can produce, we need the enthalpy now. And the enthalpy under standard conditions is 890 kilojoules per mole. It's worth saying there's a minus sign here. That minus sign just tells us that we need to put energy, tells us that energy is naturally released by combustion. Combustion doesn't take energy into the surroundings, it releases energy. So there's a minus sign there. But for our purposes, we don't really worry about the minus sign. We just want the amount of energy released per mole. So 890 kilojoules per mole. It's worth saying, however, this is the enthalpy under standard conditions. The sun being hot, at its surface it's about 6,000 degrees Celsius, so it's incredibly hot. In its core, it's more in the order of, like a million degrees Celsius, or maybe 10 million, something like that. So the sun is incredibly hot, meaning that we can't really trust this value for the enthalpy. But it gives us a ballpark. And, if you want to, you can look at hypothetical suggestions of what the enthalpy might be like in much hotter environments, and then go through a similar analysis to what we've done and see what number you end up with for the maximum output energy of this hypothetical hydrocarbon star. But we're going to use this value and it gives us a ballpark. It's worth saying that kind of like a place where chemistry and physics are currently meeting is looking at how things like the enthalpy of a reaction changes when that reaction is occurring in very different conditions to standard conditions, such as in stars and stuff. So, understanding how chemical reactions occur in space and in astrophysical phenomena or objects is an active and ongoing area of research, which is quite fascinating. But anyway, we can take this enthalpy change of combustion, and we multiply it by the number of moles, and we can see that we'll end up with something then with units of kilojoules, in other words, energy. So it turns out that the maximum energy output of the sun is going to be 1.1 times 10 to the 36 kilojoules. And if we divide this by the luminosity, as we will in the next slide, we'll be able to work out how long the sun could possibly be producing energy for if it was always producing energy at its current rate, and the manner in which it produces energy is by just combusting its material, assuming the entire star is made out of this methane. So we had before the total amount of energy the sun could produce. If it was essentially producing through just combustion hydrocarbon methane. And we can divide this by the luminosity of the sun. When you do that, you'll end up with the lifetime of the sun. I wrote lifetime because I'm assuming, due to the mass of the sun, as is reasonable, the moment the sun runs out of energy, it won't be able to support itself and it will collapse. And, the star will stop being, a stable sun. In fact, stop being a sun as we know it. So in that sense, the lifetime of the sun is just the maximum energy output divided by the rate at which it outputs energy. And that gives you 2.9 times 10 to the 12 seconds. But that's very hard to kind of understand what that number means, because that's a very large amount of seconds. So a trick in physics is, if you get a large number of seconds, particularly in the context of astrophysics, convert it into years. So if we think about, a year being approximately 365 days, 24 hours in a day, and each hour has 60 squared seconds, then you can work out how many seconds there are in a year, and it's about 3.2 times 10 to the 7 seconds. And so if we divide the lifetime of the sun in seconds by the number of seconds in a year, we'll get the lifetime of the sun in years, which is about 9.1 times 10 to the 4 years. And so, to summarise, essentially the lifetime of the sun is approximately like 10. It's approximately like 10 times 10 to the 4 years. So it's approximately like 100,000 years, which is quite long. I mean, at least compared to even ancient history, 100,000 years is a very long time. I could be wrong, but I think the first well-known human civilizations, like large-scale civilizations, go back to, I think, about 10,000 BC. So, about like 12,000 years ago. So, 100,000 is a long time, but in terms of astrophysics, that's virtually no time at all. That's even less than a million years, and a million years for stars is practically, inconsequential. So this calculation that we've done, essentially mainly just using arithmetic and GCSE chemistry, tells us clearly that unless the sun is 100,000 years old, and we know it's a lot older than that, the sun, to still be around, can't be a ball of methane combusting, unless it used to be a lot heavier and had a lot more methane to start with than it's left with now, which might make you worry, oh gosh, what if that's true, and the sun only has 100,000 years left. Well, the good thing is none of us will be here in 100,000 years. But the other thing is kind of like, the sun's mass, because there isn't really anything in the vicinity of the solar system to increase the sun's mass substantially, because we would know about it if there was. It'd be so massive. Because of that, there's no real way the sun could have had a lot more mass initially than it does now. But by kind of like, for example, initially having collected a lot of mass and then combusted some of it, such that the mass at least available for combustion now is a lot less than when it began. And also, as I say, from spectrum, we know that the sun isn't mainly composed out of hydrocarbons, so from spectral we know that this is a possibility anyway. But it's worth bring this up because we've shown legitimately that, stars wouldn't live for very long, at least unless they're like, it have to be something like, 1,000 orders of magnitude, 1,000 times bigger than the mass of the sun if they were producing energy through combustion of a hydrocarbon, even if we assume to be as idealistic as possible for this hypothesis that the entire star would be made out of a hydrocarbon. Um, um, and therefore we know that stars can't be producing energy through combustion of hydrocarbons. At least that can't be the main process. The main process turns out to be nuclear fusion, and that will bring us to using equals mc squared. So we'll now go through a similar calculation in terms of the lifetime of the sun, at least its current stable phase, so the lifetime for it to keep doing what it's doing, but using the hypothesis of nuclear fusion, which is the currently accepted version for how the sun is producing energy. So we've talked about the hydrocarbon star. Now let's talk about our sun from the perspective of kind of current standard views on how the sun produces energy. So the current main idea for how the sun produces energy is through nuclear fusion. I'll probably at some point do a playlist on the life cycle of stars and talk about nuclear fusion in the main sequence in greater depth. But essentially, nuclear fusion is where the sun combines together light nuclei, which in the sun's current phase, its main sequence phase is hydrogen nuclei, and combines them to make heavier nuclei. So for the sun, that's mainly helium. It's often simplified in schools and stuff to be just helium. That's not quite true. And definitely in larger masses in larger stars than the sun. I mean, stars with more mass, which are on the main sequence. It's not actually through hydrogen being fused to helium that most of the energy is produced. But in our sun, the vast majority of energy is produced by hydrogen being converted into helium by kind of combining hydrogen nuclei together to make helium nuclei. But if you look at the mass of the hydrogen nuclei that you combined and the mass of the helium nuclei you get, you'll find that there's a mass difference. And that's because during this fusion process, actually some masses are lost and that mass is converted into energy. And from our video on E equals mc squared, we know that you can convert mass to energy, so the mass loss can be converted into energy, and the energy we can get from nuclear fusion is going to be equal to the mass lost times c squared, where c is the speed of light. So this is where the equals mc squared equation comes in. But to do this, we're going to have to, you can use theoretical models, and also now we've done nuclear fusion processes on Earth, you can also use now actually experimental data to work out how much of the mass is lost when you combine hydrogen nuclei to make helium nuclei, so that we can get experimentally as well as theoretically. But we need to firstly know how much kind of hydrogen is present in the sun that can do fusion. Now, the thing with the sun is the sun is very hot, but it's not hot enough. Most of the volume of the sun isn't hot enough for fusion to take place within that volume. And you need really, really high temperatures, because for fusion to happen, the hydrogen nuclei have to get close enough together that the strong nuclear force, which kind of holds nuclei together, can start to kick in and fuse the hydrogen nuclei to make a helium nucleus. But before the strong force can kick in, the dominant force is electrostatic repulsion. It's repulsion because all nuclei are positively charged, so these hydrogen nuclei are repelling. So unless they have tons of energy to start with, they're not going to be able to get close enough together before they just fly apart for the strong force to be able to act and fuse the hydrogen nuclei together. So you need really high temperatures to allow really high kind of kinetic energies of your nuclei. Or we could say of your protons, because a hydrogen nucleus is just a proton. And the temperatures really only get hot enough to in other words, the corresponding kinetic energy of the protons is only large enough when we're looking at kind of the core of the sun. Now, the sun, unlike the Earth, isn't like a fairly solid object which is kind of like broken up into neatly separated layers. So there's a lot of approximations that go on with astrophysics, and the boundary with where the core starts is a bit blurry. But on average, about 20% of the mass of the sun is the kind of main core, where nuclear fusion can take place. Now, strictly, the core is about 30% of the mass of the star, but the kind of outer edges of the core aren't really hot enough for nuclear fusion, so there's a lot of approximations that go on, but we can kind of go, at least as far as the active core is concerned, the core, which is kind of where nuclear fusion is taking place, that accounts for about 20% of the mass of the sun. And we know the mass of the sun was 1.99 times 10 to the 30 kilograms, so if we take 20% of that, we end up with the mass of the sun's core being about 3.98 times 10 to the 29 kilograms. So that's the mass of the core where nuclear fusion can take place. And the mass of hydrogen in that core is about 70% of that core's mass. And we get 70% because from spectra we can go, well, the sun is about 70% hydrogen and about 30% helium, and because it's kind of a fluid, elements can freely move to a large extent within the star, so we expect the star's chemical composition to be well mixed. So, the general ratio of hydrogen to helium in the sun should also be reflected in the ratio of hydrogen to helium in the core. So if we take 70% of the mass of the core, we get 2.79 times 10 to the 29 kilograms. So that's the mass of hydrogen which can get involved in nuclear fusion processes. And the amount of mass that is actually lost during hydrogen fusion is about 0.8% of the kind of mass of the hydrogen reactants involved in this fusion process. So if we take 0.8% of the hydrogen in the core, we get the essentially maximum mass of material, hydrogen material, the sun currently has, which it still has available to convert into helium. Oh, sorry. If we take 0.8% of the mass of hydrogen in the core, we can get the amount of mass that the sun can lose over its future time on the main sequence and convert into energy to keep it self-stable. And that maximum amount of mass it can lose, based upon the mass of hydrogen it has available, is 2.2 times 10 to the 26 kilograms. So, the sun can keep, we say burning hydrogen, really meaning doing nuclear fusion with hydrogen, as long as, some of this 2.2 times 10 to the 26 kilograms, can keep doing this, and by the time it's fused all the hydrogen, it will have converted 2.2 times 10 to the 26 kilograms directly into energy. And the energy produced is equal to the mass loss, so 2.2 times 10 to the 26 kilograms times the speed of light squared, and the speed of light is roughly 3 times 10 to the 8, and when you do that you'll get the energy that the sun can produce, starting now to when, when all the hydrogen in the core has been fused. The total amount of energy the sun could produce would be 2.0 times 10 to the 43 joules. So we have the total amount of energy the sun can produce, and we can divide that by luminosity, much like we did before with a hydrocarbon star, to get a kind of time scale for lifespan of the star, or an order of magnitude of kind of the main sequence phase. So using a very similar technique to what we did before, we get that the sun could continue fusing hydrogen and producing energy through that at the rate it is kind of emitting energy, and therefore remain stable for about 1.4 billion years. Now, if we would do the calculation, taking into account more technical details and going into more depth, because we tried to use fairly straightforward arithmetic, although large numbers, we haven't tried to get too complex with, stellar structures and that kind of thing. We would actually, if we would be more accurate, we would get about 5 billion years. So the sun has about 5 billion years left, but we can see from our analysis, the sun has in the order of about, has billions of years left. More accurate answer would be 5 billion years. Now that's considerably a lot longer than hydrocarbon stars would be stable for. From everything we know about the sun, this kind of timescale for how long it's got left, and if we trace back time, considering how much hydrogen it might have been able to convert up to this point, and therefore how long it might have lived for in the past, makes, the nuclear fusion hypothesis entirely plausible, and it is the standard view for how the sun produces energy. I don't think it's ever going to change. We might add more technical details to the picture, but one should always be open. One should never go, well, this is in a textbook, therefore this is true. No, one should always be open to new ideas and challenging one's beliefs. But it's essentially thanks to the huge amount of energy you can produce by nuclear fusion that nuclear fusion can allow stars to live for such a long period of time, or be stable in the main sequence for so long, because see, the speed of light is so large, E equals mc squared means for a tiny bit of mass you get tons of energy out. So in short, nuclear fusion is a very efficient way of, well, a very bountiful way, I should say, of producing energy, because for a tiny amount of mass lost, you get huge amounts of energy released, meaning that stars, even though they emit tons of energy, can actually, keep emitting energy for a very, very long time if they're getting energy through nuclear fusion. So this was kind of a bit of an application of E equals mc squared. It's worth saying here there was a lot of arithmetic. If you don't like so much arithmetic, don't worry, most of my videos use more elegant mathematics, but given the last video was quite abstract, I thought it'd be nice to have a video about something more familiar like the sun, and use less integrals and more division signs. So, it's hopefully a nice break in that sense from more abstract concepts. Or, it's like if you want to have a more full understanding of y equals mc squared, there's a video done recently, check out. Um, uh, but also at some point I will almost certainly make a playlist about stellar evolution and talk about nuclear fusion in more depth, because I know, haven't gone through it too much in detail here, but it's, the main purpose of this video is to explore why we need E equals mc squared to describe very important things like how stars can live for so long, the order of billions of years. So I hope this video has been helpful, entertaining, and hopefully, some cool and interesting content. And as ever, if there's anything you would like me to work on or improve, or any topics you would like me to cover that I haven't covered in my other videos, or topics that you think I should go over or explore in more depth, please let me know in the comments. And I wish you a very good week, and hopefully see you for some more cool physics and possibly a dash of chemistry soon.